At work or home, you have a bunch of devices: computers, printers, TVs, and so on. You connect these by means of a network. When the devices are connected, they're able to share data. This could be sending a print job to a printer, sending an email, or streaming video. This can also be used for sharing an internet connection. Mostly, network users are unaware of the network they're using. As long as they can browse the internet, do their job, browse YouTube, they're usually fine. For all of these devices to communicate, they need to be connected together somehow. One way is to plug cables into the devices and connect them to another device called a switch. An example is in a school's computer lab. In this case, a computer in the lab connects to a wall socket with a cable. Another cable runs through the wall, which comes out at a patch panel. This may be in a cabinet on the wall somewhere in the room, or in another room entirely. The port on the patch panel then connects to the switch. You might have a switch at home too. Most homes don't have wall sockets, so devices are connected directly to the switch. We'll talk more about how switches work later. We can also connect devices wirelessly. A common way to do this is to use a wireless access point. A wireless network like this is also called Wi-Fi. An example of this is if you have a tablet. It is impractical to cable it in, so wireless is a good option. The access point is like a switch without cables. More than one device can connect to the access point at a time, but without the messy cabling. The access point can also be connected to the switch with a cable. This way, wired and wireless devices can all be part of the same network. Having both wired switches and wireless access points gives you more connection options. Imagine you have a laptop in an office. You may connect it to the network with a cable when you're at your desk. When you have a meeting in the conference room, you remove the cable and connect to Wi-Fi. Whether wired or wireless, the goal of the network is to move information from one device to another. For this to work, the sender and the receiver must understand each other. They need to speak the same language. In the network, speaking the same language means that devices agree on how data is sent, received, organized, and handled. Basically, they agree on a process that they all follow. It's a bit like filling out paperwork. This is called a protocol. A lot of different protocols are used depending on what's needed at the time. Network software and hardware are designed with these protocols in mind. You will hear of protocols like Ethernet and TCP, which are used for sending and receiving data. You may also hear of protocols like HTTP, which is used for accessing the web, and SMTP, which is used for email. Usually, several protocols are used together to achieve a task. We'll look at protocols further in future videos. In summary, networks are used to connect devices together. Devices use the network to communicate and to share information. To share information, devices need to speak the same language. This language is called a protocol, which is a set of instructions of how to handle the information. Networks connect devices. You could call devices on the network nodes. Nodes may include devices that help control the traffic flowing through a network, like switches and routers. Nodes also include endpoints or hosts. These are devices that send and receive the bulk of the traffic. This includes workstations, servers, printers, and so on. Networks come in different sizes. A network at home is an example of a small network. These networks usually only have a few nodes. This is called a SOHO network. SOHO means Small Office Home Office. These networks typically have a couple of computers, a printer, a few phones and tablets. Some devices will be wireless, and some are connected to a switch. This might be a good time to mention that people often say hub when they mean switch. You can see why, of course, as the switch looks like a central hub in a SOHO network. But please keep in mind that switches and hubs are very different things. Hubs are really old technology that you generally don't see anymore outside of a museum, while switches are modern and commonly used. They look very similar, so it's easy to mix them up. Have a look at the model number to see if it gives you any clues about what the device really is. In a SOHO network, a router is used to connect to the internet. You might find that the router, switch, and access point are all integrated into one device. While a SOHO network will only have a few devices, a corporation, for example a bank, will have many devices. This is called an enterprise network. The enterprise network may cover several floors in a building. They may also have several office buildings in different cities or even across different countries. An internet provider has a very large network. This is called a service provider network. Not only do they provide internet access, they also offer services to connect their customers together. Consider the bank with offices all around the country. The service provider uses part of their network to join these offices together. When devices are collected into a local area, we call this a local area network, or LAN. The LAN may be a small network. In a SOHO network, the LAN is the switch with a handful of devices connected. Or the LAN may be part of a bigger network, like an enterprise network. This network may have many switches, routers, and access points, depending on their needs. Think of the bank from before. They have an office with several floors. You could consider the whole building as a LAN. Or, more likely, the network is broken up into smaller parts. Perhaps there is a separate network on each floor. Each of these could also be called a LAN. These separate LANs may be connected together, but we'll talk more about that later. But a bank's network is going to be larger than just one building. Banks have offices all over the country and all over the world. Even though they are far apart, these networks can be joined together. This is called a WAN, or Wide Area Network. Imagine for a moment that you work for a company with an office in Sydney and an office in Melbourne. You could contact a service provider and they can connect these offices for you. WANs are a topic all of their own, so we'll cover them in detail in a later video. Let's take a moment for a quick summary. All networks are different, and this includes their size. A SOHO network is very small, while an enterprise network may be very large. Of course, your network could fit in anywhere in between. A LAN, or local area network, is a collection of network devices in a local area, like a single building. A WAN, or wide area network, connects networks that are far apart. When it comes to connecting devices, there are two options, wired and wireless. Wired connections have been around since the beginning of time. That's the late 1960s as far as networks are concerned. A wired network uses cables to connect devices together. Wireless technology in general has existed for a long time. Think of radios and mobile phones, for example. The wireless technology that we think of most with networking is called Wi-Fi, which has been around since the early 1990s. Cables can be copper or fiber. Copper cables are usually cheaper and are very common for short distances. Data is sent over copper cables using electrical signals. This means that they can be affected by outside interference. I'll explain why this happens a bit later. Fiber cables are made of strands of glass. Data is sent through the fiber in the form of light. Fiber is more expensive, but is really good over longer distances. Also, it is not affected by outside interference. A wired LAN uses a protocol called Ethernet. Remember that a protocol is a set of rules that devices in the network agree on. Ethernet is made up of a lot of different parts. Some of these parts describe types of cabling and the speeds that they run at. Other parts describe how the data should be formatted and sent. This is called media access control. The reason Ethernet is layered like this is so devices with different cables and different speeds can all still communicate. Imagine a workstation that has a 1 gigabit connection to the network. It wants to send data to a server that has a 10 gigabit connection. The workstation prepares a message. It formats it according to the media access control rules. Then, it prepares to send the message according to the physical rules that it has to follow. When the server receives the messages, it decodes it at the physical layer. The message that is left is the same as it was at the workstation's MAC layer. As you can see, even though they have different connections, the hosts can still communicate because of this layering system. Ethernet was designed by a group called IEEE. IEEE have created many different standards for different technologies. All of their standards have a code number. Standards that start with 802 are used for LANs. Ethernet, for example, is 802.3. Remember how Ethernet is a group of standards? Each of these is assigned 1 or 2 letters. For example, 10 gig Ethernet is 802.3AN. If you'd like to see a full list of Ethernet standards, have a look at the Wikipedia page on IEEE 802.3. Codes like 802.3AN can be tricky to remember, so each of these physical standards have friendly names, which are a bit easier to understand. For example, 802.3AN is also known as 10G base T. This gives us a bit of a hint about what the standard is. The 10G refers to the speed of the connection. In this case, it is 10 gigabits per second. Base is short for baseband. This means that it uses a digital signal. The alternative is broadband, which uses an analog signal. The T means that this is a UTP cable. I'll explain what a UTP cable is soon. You might see other cables here, like LX, which refers to a type of fiber optic cable. Electrical cables use electrical signals. These are a pattern of 1s and 0s. The receiver needs to decode this pattern. The pattern is called an encoding scheme. To send electrical signals, a circuit is needed. This means that electrical cables need to contain several wires. The most common copper cable is called unshielded twisted pair, or UTP. Modern UTP cables contain 4 pairs of wires, where each pair forms a circuit. Electrical signals over copper cables can be disrupted by interference. Think back to high school science for a while. Do you remember that electricity and magnets are related? Electricity flowing through a copper cable creates a magnetic field. A magnetic field and a copper cable can create electricity. The problem is that a pair of wires running parallel create a small electromagnetic field. The field from one pair of wires can affect the signal on another pair of wires. This is called crosstalk. UTP eliminates most crosstalk by twisting the pairs of wires together. Each pair is no longer running in parallel, so they don't generate the field. If you can, find an old network cable that you don't need. Cut the end off it and strip back the plastic around the outside. You'll probably find 4 pairs of wires, depending on how old the cable is. There may also be a plastic core or a piece of string. They're color-coded, so each pair has a solid color and a striped color. For example, one pair will have brown and striped brown wires. Now I said that you will probably have 4 pairs. There wasn't always 4 pairs though. Older Ethernet standards, such as 10 base T and 100 base T, only needed 2 pairs. But to achieve 1 gig and 10 gig speeds, all 4 pairs are needed. Not only are there different Ethernet standards, but the cable itself has different standards. You will hear of terms like Category 6, or simply Cat 6. The category defines things like the number of pairs in the cable, the thickness of the wire, and how tightly they're twisted. For example, Cat 2 has only 2 pairs. Cat 6 has 4 pairs. Cat 6 has thicker wires than Cat 5, and so on. Sometimes there'll be an E or an A at the end of the name. Cat 5e and Cat 6a are examples of this. This is where the original standard has been improved upon. Newer standards support better speeds over longer distances. For example, you can use a Cat5 cable on a 100 meg network. But if you want to run a gigabit network, you need at least Cat5e. If you want 10 gig, Cat6 is okay up to around 55 meters. But if you run Cat6a, you can have a 10 gig link that works up to 100 meters. Each newer standard is backward compatible with the older technology. For example, you can use a Cat7 cable on a 100 meg link. Your cable has a connector at both ends. This is called an RJ45 connector. This is the part that you connect to your network card or switch port. This connector has 8 pins. These line up with the 8 wires inside the cable. The wires need to line up with the correct pins. That's why the wires are color-coded. There are different color schemes you could use. This one here is called 568B. A standard UTP cable will match the wires on both ends. This means that pin 1 connects to pin 1, pin 2 connects to pin 2, and so on. This is called a straight-through cable, as the wires go straight through from one end to the other. Some pairs are used for transmitting data, and others are used for receiving. For example, pair 1 transmits, while pair 2 receives. You'll see here that I've used the terms RX and TX. These simply mean receive and transmit. When you connect a host to a switch, the switch does something very clever. It knows that pair 1 is used for transmitting and pair 2 for receiving. So it does the opposite. It uses pair 1 to receive and pair 2 to transmit. So when the host sends on pair 1, the switch receives on pair 1. The same logic is used on pair 2. The key point here is that a straight-through cable is used to connect a host to a switch. But what if you want to connect a host to something that's not a switch? Perhaps another host or a router? The pins no longer line up correctly. They are both using the same pairs for receive and transmit. So instead, we need to use slightly different cables. What we do use is a crossover cable. This swaps the pairs at one end, so transmit lines up with receive once again. This is also the type of cable you would use if you want to connect one switch to another switch. The alternative to copper cabling is fiber cabling. Fiber cables use strands of glass, which are sometimes called a pipe or a core. A light pulses down the fiber strand, which is received at the other end. Fiber is often used between networking devices, like routers and switches. It may also be used in servers. I've never seen workstations use fiber, but I guess anything's possible. I'm going to take a quick detour and talk about something called duplex. Devices need to both send and receive data. UTP cables can send and receive at the same time. If both ends of the link support this, it's called full duplex. Sometimes a device will not be able to send and receive at the same time. Instead, it will send for a while, stop, and then receive for a while. This is called half duplex. These devices can still send and receive, but they can't do both at once. Full or half duplex is determined by the cabling that's used, the capabilities of the device at both ends of the link, and the software configuration. There are two different ways that fiber can be used. First, you can use single core only. This operates in half duplex mode, as it can't send and receive at the same time. The other option is dual core. This is full duplex, as one core is dedicated to sending and one is dedicated to receiving. Be aware though that it's easy to get the cores mixed up. If you connect the fiber and it doesn't work, try swapping the cores at one of the ends. The enterprise network will mostly use dual core fiber. This means between switches, routers, and servers. Service provider networks, like your internet and WAN providers, often use single core. Now you need to be aware that there are two types of fiber. These are called single mode and multi-mode. They may look the same, but they are different because of the types of light they use. Multi-mode, which is known as MMF, uses a LED light. This is not a particularly powerful light, so it is used over shorter distances, say around 500 meters or less, which makes it useful to connect devices in the same building. The LED light is also cheaper to produce, making multi-mode fiber the cheaper option. Single-mode fiber, or SMF, uses a laser light. This makes it more expensive, but it is capable of much longer distances. You could easily get 2 kilometers or more depending on the hardware you're using. You would typically use single-mode fiber between different buildings. Or your service provider may run single-mode fiber into your building to give you WAN or internet access. Even though a fiber optic cable is made of glass, it is still flexible. You can bend the cable. Well, at least to a point. The fiber cable has a maximum bend radius. The bend radius is how tightly the cable can be coiled up before attenuation occurs. Attenuation is where the signal is degraded or lost. This does not necessarily mean that the cable won't work, but it won't work well. The manufacturer of the cable should be able to tell you what an acceptable bend radius is. There are different connectors that the fiber cables may use. Quite a few, in fact, when you remember that fiber is not just for networking. The main ones we see in data networking are called LC and SC. LC are the smaller connection types, which are usually used on switches and routers. It's common to see these in a dual-core configuration, but they can be separated into single-core. SC connectors are older and larger. They seem to be less common these days. They're more often seen in a wiring closet. Some switches will have a special port that looks empty. Some switches are made up entirely of these ports. These are made for installing a transceiver module. These can be used for different purposes, but basically, they are so you can mix and match the type of cabling you use. Different transceivers support a different cable type. This includes single-mode and multi-mode fiber. Some transceivers will support both, but they also support different speeds, like 1 gig or 10 gig, as well as different cable lengths. For example, a long cable run of 40 kilometers will need a more expensive transceiver than you will need for a 1 kilometer run. The reason that some of these switches have many of these ports is so you can mix and match which transceivers you use for the job. You can even use an RJ45 transceiver for when you want to use UTP copper cable. Wireless, aka Wi-Fi. It doesn't use cabling, of course, but I should mention it quickly anyway. Wireless networks use access points. These devices are like a switch for the wireless network. Wireless devices like your phone or laptop connect to the access point. The access point may also connect to the wired network. This is how wired and wireless devices can be in the same network. Wireless is a good way to connect end-user devices. You wouldn't normally see a server or router connected to an access point. Wi-Fi does not use the 802.3 Ethernet standard. Instead, Wi-Fi uses the 802.11 standard, which was also created by the IEEE. This describes how radio waves are used to format and encode information and to get different speeds. While they're not the same, Ethernet and 802.11 do share many similarities in the way data is formatted, but that's something we can look at another time. Let's have another quick summary. Networks can be wired or wireless. Wired networks may use copper or fiber cables. In a wired LAN, the Ethernet standard is used to describe how data is formatted. It also covers cable types, link speeds, and how to encode data on the physical link. UTP is the most common copper cable. Modern UTP cable has 4 twisted pairs of wires. Some are used for sending, and others are used for receiving. The cable may be straight through, for connecting devices to a switch, or it may be crossover, for connecting devices to each other. Modern LANs support Auto MDIX, which enable the device to detect the cable used and adapt as needed. A full duplex device can send and receive at the same time. A half duplex device can only do one at a time. An example of this can be found in fiber cabling. Dual-core fiber is full duplex. Single-core is half duplex. If you want a short and cheap fiber run, you can use multi-mode fiber. If it has to be longer, you need the more expensive single mode. You also need to use the right transceiver in the device you're connecting the fiber to. If cables aren't going to work for you, then you can consider using wireless access points to create a wireless network. Let's go back to our SOHO network for a while. We use diagrams like this to show how a network fits together. Notice that this is the logical view of the network. It doesn't show all the physical details like the number of switches used, the type of cabling and so on. It's just a simple way to show how things fit together. Imagine that the computer wants to send a print job to the printer. The printer is network enabled, so the computer can send a print job over the network. The network has several endpoints, so how does a computer know where to send the data? Could it just send a message to everything on the network and hope that the right device knows what to do? Well, this does happen on occasion. But if this happened all the time, the network would be very inefficient. Imagine if all the endpoints were sending at once. Also, this could be insecure. What if this was private information? All the other endpoints would see it. And what if there are several printers? Which one would accept the print job? Or do they all start printing? No, the print job needs to be sent only to the correct printer. But how does this happen? Each device on the network has an address. This is like your home address. Your address is unique, and it enables others to find you, contact you, and deliver packages. In a LAN, each device has two addresses. They each have an IP address and a MAC address. These two addresses are used in different ways. We're going to have a brief overview of these addresses here, and dig into more detail in later videos. Let's start with MAC addresses. Each host has at least one MAC address. To be more accurate, each network card has a MAC, so multiple network cards means multiple MACs. When the network card is manufactured, the MAC is permanently assigned. We can't change it. This is also known as the burned-in address. As each network card has its own MAC address, each MAC is guaranteed to be unique. A MAC address is used when one device needs to communicate with another device in the same LAN segment. I'll explain what I mean by this soon. Each device also has an IP address. This address is chosen by us, the network administrators. When we choose addresses, we can make them easier to remember. We also use IP addresses when one device wants to communicate with another, but IP addresses are special, as they allow us to access hosts on a different LAN segment. Imagine that our small company has been very successful and has now grown. Rather than just a single network, we have decided to create a second network. Each of these networks is a LAN segment. These are joined together with a router. This router is part of both LAN segments, so its job is to pass network traffic from one segment to another. MAC addresses are used within the local LAN segment, so when we send a message to, say, a printer in another network, we can't just use the MAC address of the printer. IP addresses, though, are different. We can use the IP address of the printer when we want to send it a message. Let's see how this works. The computer prepares a message for the printer, and it adds the printer's IP address. The printer is on another network, so it needs help to deliver the message. The computer knows that the router can help, so it adds the router's MAC address to the message and sends it. The router receives the message and strips its own MAC address off the message. In its place, it puts the printer's MAC address on instead. The router then forwards the message to the printer. This may raise a lot of questions for you, but don't worry, we'll look at how this works in more detail another time. For now, just remember these things. Hosts have a MAC address and an IP address. A MAC address is used only within a LAN segment. An IP address can be used within a LAN segment, but is also used to pass traffic to a different LAN segment.